Welcome to another Explainer. I'm so thrilled you're here today because we are tackling something incredibly fascinating. We're looking at the invisible, highly structured architecture that quite literally runs our modern world. Have you ever wondered how machines actually manage to make complex, calculated choices when the real world they operate in is completely chaotic, messy, and totally unpredictable? Well, that is exactly what we're unraveling today, looking at foundational concepts from the textbook Algorithms for Decision-Making.
Okay, let's dive into this. How do we teach a machine to navigate the unknown? We're going to go on a journey today, starting from massive, high-stakes, real-world applications and working our way all the way down to the elegant core mathematics that make those applications possible. It is a brilliant blend of computer science, operations research, and probability.
Let's kick things off with Section 1, High Stakes Under Uncertainty. When we talk about algorithmic decision-making, this isn't just some abstract theory being debated in a dusty lecture hall. This is about real-world survival and critical, life-altering outcomes.
Just think about the sheer scale of these applications for a second. When an automated system is handling aircraft collision avoidance, it has to rely on incomplete, noisy radar data to prevent mid-air disasters in a matter of split seconds. Or consider Mars exploration. Rovers on Mars face up to a 30-minute communication delay with Earth. They literally can't wait for human to tell them how to avoid a sudden cliff. They have to decide for themselves. From coordinating swarms of drones for wildfire surveillance, where the wind is constantly shifting, to personalizing breast cancer screening schedules to balance false positives with early detection, these algorithms are managing massive uncertainty with absolutely zero room for error.
So, to solve these planetary scale problems, we have to look at Section 2, the anatomy of a decision. We need to zoom way in to the fundamental brain of the machine.
Look at this observe-act cycle right here. It is the absolute core of the whole process. You've got the agent, whether that's a Mars rover or a medical diagnostic tool, and you've got the environment. The agent receives observations from the environment, but those observations are almost always noisy or incomplete. Based on that imperfect data, the agent takes an action, and here is the kicker. That action physically changes the environment, creating a brand new state, and the entire cycle just repeats itself.
Now, what's really wild is breaking down the exact hurdles the agent is facing in that cycle. We can categorize this into 4 distinct types of uncertainty. First, outcome uncertainty. The agent doesn't even know for sure what it's actually going to do. Second, model uncertainty. Maybe the agent's internal map of how the world works is just flawed. Third is state uncertainty. Imagine a drone flying over a wildfire not knowing exactly where the fire line is because of heavy smoke. And fourth, interaction uncertainty. Just think of the sheer unpredictability of other agents, like a self-driving car trying to guess what a human driver is going to do next.
So, where did we get the tools to actually solve this? That brings us to Section 3, A History of Automation. We didn't just wake up with modern AI. It's a stunning tapestry of completely different sciences merging over centuries. The dream goes all the way back to the ancient Greeks. Around 800 BC, Homer was literally writing about automated mechanical tripods serving dinner guests in the Iliad. But the math really started taking shape in the 18th century with economics and the invention of utility theory, a way to mathematically weigh how desirable an outcome is. Jump to World War II, and you see the birth of operations research for military resource allocation. Right around that same time, neuroscience gave us the concept of neural networks. All these completely disparate threads, mythology, economics, military strategy, and biology, they all merge together to give us the algorithms we use today.
Let's move into Section 4, the math of uncertainty. We've talked about the high stakes and the history, but how does the machine actually think about the unknown?
The absolute crucial mathematical tool here is the probability distribution. This is the exact framework an algorithm uses to quantify its uncertainty before it acts. Simply put, it's a function that assigns probabilities to different outcomes, and crucially, all those probabilities have to add up to 1. It is the mathematical language that allows a machine to say, hey, I am 80% sure the path is clear and 20% sure there is an obstacle.
And this brilliantly illustrates that concept. Notice those distinct separate bars. That is a discrete probability mass function. It's perfect for variables that can only take on specific distinct values. Think of rolling a 6-sided die. You can roll a 1 or a 2, but you cannot roll a 1.5. The algorithm just calculates the probability mass for each distinct jumping outcome.
But let's see how this builds into the real world. Because while discrete math is great for games of chance, the real world doesn't usually move in neat little jumps. Predicting the exact altitude of an aircraft
or the velocity of a car requires measuring continuous realities. There are infinite possible values between 1 and 2. To handle that, we use continuous probability densities, like the uniform distribution. I want you to notice that flat horizontal line right across the top. Let's say that continuous range is between 0 and 10. In a uniform distribution, every single value in that range has an absolutely equal probability density. The machine is essentially saying the outcome could be literally anything between 0 and 10, and I have absolutely no mathematical reason to favor one number over another. Now, contrast that flat line with this sweeping bell curve. This is the famous Gaussian or normal distribution. That peak right in the middle represents the most likely outcome. And this is a real game changer for autonomous agents. If an automated vehicle is tracking a pedestrian, it might use a Gaussian distribution to predict their path. The peak is the most probable trajectory, while the tapering edges represent less likely but still very possible sudden movements.
But let's be real, the world is rarely just about tracking one single thing. A univariate distribution models just one variable. But a multivariate joint distribution allows the machine to model complex, overlapping relationships between many variables at once. What's the probability that it's raining, and the pedestrian steps into the crosswalk, and your brakes are slightly worn down? Joint distributions allow the algorithm to connect all those uncertain dots to make a single safe decision.
All right, let's zoom back out to the big picture with Section 5, Impact, Bias, and Society. When we optimize systems globally, the impacts are vastly magnified.
The societal benefits we're looking at are truly monumental. These algorithms are driving environmental sustainability. They're optimizing smart grids and managing habitats to protect biodiversity. In medicine, they're revolutionizing disease diagnosis, acting as this incredibly powerful second set of eyes for doctors to catch anomalies way earlier than a human ever could. And they're quietly running in the background of our cities right now, making urban infrastructure smarter and massively improving emergency response times.
At the same time, we have to look neutrally at the systemic challenges and risks here. Algorithms are literally only as good as the data they are fed. If there are inherent biases in the training data, the system might simply replicate those blind spots in areas like housing or loan approvals. They're also vulnerable to adversarial attacks, where bad actors can subtly manipulate inputs to trick the system. And then there is the alignment problem, the sheer technical challenge of unintended consequences. An algorithm optimized strictly for user engagement might inadvertently amplify misinformation just as easily as helpful content, simply because its mathematical goals weren't perfectly aligned with the broader intent of its human designers.
If such a problem could be successfully solved, it could eventually, through better planning, contribute to the well-being and stability of the world. That profound thought comes from George Dantzig in 1991. He was the legendary mathematician who developed the simplex algorithm. Reflecting on the monumental challenge of dynamic planning under uncertainty, his words perfectly capture both the immense technical responsibility and the profound hope tied up in this math.
And that leaves us with the ultimate question. As these algorithms get better and better at learning to navigate the unknown, how do we ensure they continuously align with our intended goals? We have given machines the mathematics of uncertainty, but it is entirely up to us to define the certainty of their purpose. Definitely something to think about the next time a piece of software makes a recommendation for you. Thanks so much for joining me on this explainer. I hope you found it as fascinating as I did. Keep learning, and I'll catch you next time.